Good morning, my fellow scientists. It is Tuesday, April 18th, 2017, and I want to talk a little more about iron batteries. First off, I want to say thank you to those of you who left me messages and comments encouraging me to look into battery prototyping with an iron cell for home use. I think that's an exciting subject, and I'm glad you do too. So how are we going to build an iron prototype? Yesterday, I went over the Nernst equation and how that allows us to predict the voltage on a cell using the individual half reactions that we are going to be running. So we can use that to predict the voltage on an iron cell, and then we can construct one, measure the voltage, and see if we're running the reaction we think we are. So we're going to put iron on one side of the cell, and that iron is going to get oxidized. That's the anode. And it's going to go to iron 2+. That's the first half reaction. The second half reaction is iron 3+ going to iron 2+. That reaction happens at the cathode. Each of these reactions has a characteristic voltage, either 0.44 or 0.77 volts in this case. The sum of those voltage is 1.21 volts, so when we're done constructing our cell, we should see a voltage of 1.2 volts. I'm going to start by cutting the bottom off of this cup for a reservoir for my electrolyte, and then I am going to cut a strip of paper to the same approximate height in order to make a separator. Now, paper is not the perfect separator material, but it'll do for a demonstration. It's a little less specific than, say, a polymer separator, but it'll get the job done for now. I'm going to wrap that separator membrane around a Sharpie pen and then wrap the anode wire, it's just a piece of iron wire, around the paper to hold it into the tube shape that I want. Now that I have that tube, I'm going to glue the bottom rim with a little hot glue here and apply that to the inside of my reservoir, and that should just stick. And that's going to make a seal around the bottom so that the electrolyte I put on the inside isn't going to leak out to the outside, or at least it's not going to leak out as much as it would otherwise. Now I put a pencil lead into that tube. Pencil lead is a little piece of graphite that's going to act as my cathode electrode at which metal is going to be reduced. I'll add hydrochloric acid to the outside reservoir, and then I'm going to add some iron 3 chloride to the inside. Gloves are wise, but this is only 0.1 molar hydrochloric acid, so it's not worse than stomach acid, but still, would have been wise to wear some gloves. In any case, now we're going to connect up the voltmeter to the anode and cathode. The anode is going to be that iron wire, and the cathode is going to be that piece of graphite, pencil lead that's sticking out. And then we're going to look at the voltage. I got about 0.46 volts. That's not as high as I wanted. I was anticipating about 1 volt and only got about half that. So I suspected that what was going on was there was just not enough fresh iron surface on that iron wire. So I put a little bit of iron solution on the outside reservoir and the outside electrolyte, the anode electrolyte, and then applied a bit of current to that in order to drive some fresh iron onto the outer surface. And then, when I had refreshed the surface, I did the same trick, put a little bit of iron into both sides, and then checked the voltage. And this time, got a pretty solid 0.9 volts. So, yeah, in the end, we were able to get almost 1 volt out of this very primitive cell. So there's the most primitive version of the all-iron battery. We have an iron anode. Clearly that iron wire I was using is less than ideal. Maybe it's got a little oil coating on it or something that was making life more difficult for me. So we've got to get a better iron anode, and then we need a little better cathode, because that piece of graphite has some serious resistance, and even for the really low level of current that we're trying to draw through this battery, that's clearly causing some problems. So we need to improve the anode performance, the cathode performance, and the separator itself needs a little work too, because paper is hardly ideal. We want to restrict the diffusion of the molecules of iron, but we want to allow for charge transfer in order to balance the charge in the cell. So we definitely have some more work to do, but with better materials and a larger scale system, I think we can actually power a LED. We'll probably need 3 in series to do it, but we'll work on that tomorrow, and I hope you'll join me for more projects like iron batteries, scaling up iron chemistry, and battery performance here in the Allen Lab.